Good evening, Mr. Fauzi. My name is Rashna Mohan, and today I will be talking about the introduction. So, the title of our project is Production of Ammonia. Our main objective is to produce 99.9% of ammonia from nitrogen and hydrogen gas. The process of making ammonia is called Haber process. This reaction is exothermic and irreversible. In this reaction, we used 100 kg mole per hour as our flow rate, as well as 50 degrees Celsius for the temperature and 100 kPa for the pressure. Ammonia has many uses. One of the most common ones are fertilizers. Fertilizers provide essential nutrients for plants as well as farms and crops. Ammonia can also be used for manufacturing plastics as well as dyes. Based on an article from Modern Intelligence, the global ammonia market is expected to record a compound global market of over 5%. The major factor that is driving the market is the growing demand in the agriculture industry and its increasing usage for production of explosives. That is all from me. Thank you.
Hello everyone, I hope everyone is doing good and safe. I'm Nurhan Saad. I'm going to introduce for you the production of ammonia, which is named as Haber process. For the objectives of this simulation is we used Unison to give us the best, the maximum yield of ammonia with the least cost and time, which will be sufficient for other companies to use. We have experienced different parameters like increasing and decreasing temperature and pressure and molar rates to reach the optimum temperature and pressure to reach the optimum parameters, which will be discussed later. The ammonia is produced from nitrogen and hydrogen. For this simulation, we have used 25% of nitrogen to 75% of hydrogen. Our main purpose was to produce 1,000 tons of ammonia per day with a purity of 99.9% of ammonia. We will take you through a closer look with my colleagues through the PFD steam tables and everything to give you a closer look of what we have used.
Hi guys, my name is Nina Nur Shahira and I'm here to present the design methodology of our process. We have 4 unit operation in total, which is a mixer, a reactor, heat exchanger, and a separator. Okay, now let's talk about the mixer. We have 75% of nitrogen and 25% of hydrogen going in as the feed. And then we also have the recycle stream from the separator at the end of the process. Okay, after the mixer mix our feed of nitrogen and hydrogen, we are now at a PFR plug flow reactor where the parameters of temperature, pressure, and catalyst are set to this. And now we are ready to go to a heat exchanger before separating the production of liquid ammonia and the unreacted gas. After the reactor, we are now at the heat exchanger where the temperature is now being lowered to compress the ammonia and the unreacted gas before going into a separator to separate it. Okay, after the reactor and the heat exchanger, we are now here at the separator. So at the separator, we are separating the unreacted gas from the reaction and the produced ammonia. So in order for the unreacted gas to be recycled, it will go through a heat exchanger and then back to the mixer to go through another round of reaction. And the produced liquid ammonia will now go to a splitter separator to separate out the pure ammonia produced. The reason why we separate and recycle the unreacted gas is to achieve a higher production of ammonia by not having any wastage of our feed. That's all from me today. Thank you. Hope you understand the design methodology of our process.
Hello everyone and welcome. My name is Abdurrahman. Today I'm going to present about the simulation part. In this flow sheet you're going to see a mixer. The mixer is going to mix the feed and the recycle. Afterwards you can see a reactor. The reactor reacts hydrogen and ammonia in a kinetic reaction. In this kinetic reaction, the first part is the stoichiometry. We're going to fill up the stoichiometry coefficient to make sure that it's correct, and fill the bases as partial pressure, base component as nitrogen, and reaction phase as vapor phase, and the reaction parameters from document. Now we're going to return to the simulation environment. In the simulation environment, after the PFR is the heat exchanger. In it, the material which should be cooled will flow in the horizontal line, which means it will flow from the tube side inlet to the tube side outlet. The material which should be heated will flow from the shell side inlet to the shell side outlet. This way we could simultaneously heat and cool the process. Next, after the heat exchanger, the mixture is going to flow into a separator. And the separator is going to separate it into a gas and a liquid. The liquid one is going to flow to the ammonia. The ammonia with little bit of mixture is further going to be splitted using a splitter. In this way we will get a pure ammonia of 99%. After the gas phase from the separator is separated, it will go in the shell inlet side of the heat exchanger and go to the recycle. In the recycle, we recycle the gas back to the feed to start the process all over again. Now this is for the heat integration. One without heat integration is this one. In this process, the only difference is instead of using a heat exchanger, we're going to use a cooler and a heater. In this case, it's going to be easier to specify the temperature, the outlet temperature, or specify the heat flow. In our case, the thing we specified is the outlet temperature. This is because if the outlet temperature is more than 50 degrees Celsius, the ammonia produced will go in the gas phase. Thank you.
Hello, my name is Abdulmalik Haider. I will talk about results and analysis. So first we have our feeds at 426.9 Celsius, 202.6 bar, and 1000 kilojoules per hour. For our combustions, which they are nitrogen 0.25% and hydrogen 0.25% as our inlets or feed. We have here our product, which we have the pure product, which is our desirable product, the ammonia, the pure ammonia, and we also got gases which include nitrogen, hydrogen, and ammonia. First, material stream after heat integration, and here we have this is the composition for the feed. The composition, no change between heat integration and without heat integration. we don't have energy specification for the heat exchanger. This is the energy composition for the one before heat integration. We have here stream table before heat integration, which is almost similar to the to material stream. So from the simulation we have seen that without heat integration is better than with heat integration. Thank you.
Hello and welcome. My name is Abdurrahman and I'm going to talk about the discussion. Based on the results in the simulation, we found that the difference between the process with heat integration and process without heat integration. The one with heat integration is the one with heat exchanger. The heat integration had no effect in the production of ammonia, since the heat exchanger or the heater came after the reactor but had affected the separation and the recycle. The simulation without the heat integration did better in energy conservation than the one with heat integration. This is because the amount of heat energy was specified for the one without heat integration. Now I'm going to talk about the analysis proposal. In our simulation, the one with heat integration had a conversion of 35.14% in the reaction. For the one without heat integration, the conversion of the reactor was 36.80%. This is because of the recycle coming back and mixing with the feed, which changes the conversion of the reaction. The next one we are going to talk about is the mass flow rate. The mass flow rate for the one with heat integration and the one without heat integration is similar. This is the production of ammonia. 4101.2 kg per hour is the production of ammonia for both, which is equal, since the reaction is not recycled. The last one is the energy. Energy usage was not given since the heat exchanger was overspecified, and if it was not overspecified, it was underspecified, and if it was not underspecified, it had temperature cross and FT correction factor was missing. This is the problem for the one with heat integration in our simulation. For the one without heat integration, the energy for the cooler was 3.4 times 10 to the power of 4 kilowatt and 2.12 times 10 to the power of 4 kilowatt for the heater. This is all for my part. Thank you.
After going through the discussion in the simulation file, I hope everything is clear. Finally, we have reached our target, which was 1,000 tons of ammonia per day with the 99.9% of purity. That was hard to reach, but we did it. This was the most economic way where it conserves energy and it also reduces costs, which might be used by companies. Thank you for listening and hope everything is clear. This was presented by Nurhan Saad.